today I would like to talk about a very important article of Yuval Perez and Perla Susi in 2013, and the title is Mixing Times are Hitting Times of Large Sets. So if mixing time is a very complicated thing, we can get around and use some proxies in order to get some estimates. And all of these concepts are related to each other. As you know, the total variation mixing, T-mix, is the minimum time that this distance is less than epsilon. And this is just the maximum of... so this is a measure on how close we are to the stationary distribution. And for lazy version of that, we can use TL, T lazy of epsilon. The same thing, but this is for lazy version. So PT is just P lazy of P lazy. So the transition probability is just different. And the maximum hitting time of big sets, TH alpha, where alpha is less than 1/2, is the maximum of expectation of hitting time of set A. And it can be proved that for any alpha, there exists C prime of alpha, that your T of L is greater than or equal to TH of alpha. And all of these are equivalent up to some factors, and there are many theorems in this article. For example, T lazy is upper bounded by C alpha, TH of alpha, and lower bounded by C prime of that. And for example, a theorem that says that there exists a universal positive constant C and C prime such that T average is between C prime TL and CTL. And also, so all of these things are related to each other, so we can use them as some proxies in different problems that you are solving. So each person may use a different variable. Somebody needs TL, somebody needs T average, and T average is just the minimum time that the maximum of the name suggests that we are just averaging the transition probability PT plus 1 and see how close it is to the stationary distribution. And for example, there is a lemma that says TG is upper bounded by for T stop plus 1. And this is something that is very interesting, but is very difficult to calculate and is related to filling rules and those theorems of Lovász as well. And T stop is just the maximum of minimum of expectation of for any stopping time. And I will prove a theorem about this, which is proved by Yuval Perez, although the theorem is for Lovász. So it says stopping time such that the probability that X evaluated at time at your stopping time is just the stationary distribution. And so before I prove the theorem of Lovász So the thing that I'd like about Yuval Perez is that he proved the theorems of Laplace in a very beautiful way, and we can understand Laplace much better by reading the proofs of Yuval Perez. And so any proof that Yuval Perez shows us gives a better understanding of the problem, a better understanding of the concepts. And we need a concept of halting state. For example, if we have a set A, for example, S is a stopping time, and we say Z is a halting state for stopping time if S is less than equal to time to hit state Z. So for example, starting from here, random walk, it hits here, and sometimes it goes out and hits Z. But in order to hit Z, we should get out of the border of A, or boundary of A. And the theorem that I want to prove, the Yuval Perez has proved, and I want to describe it, is that Laplace and Winkler, is that if mu and rho are two distributions, and S is just a stopping time, such that the probability that XS is equal to X is equal to rho X for all X, then S is the mean optimal in the sense that expectation of your stopping time is the minimum of all expectations of stopping times, and U is a stopping time such that the probability that XU is equal to rho. So this holds if and only if it has a stopping time. It has a halting state. As you remember, Z could be a halting state for set A. And before you understand this thing, I should recall the exit frequency concept of Laplace. That what is exit frequency is just Xi is equal to, for any stopping time we have exit frequency. It shows that these are expected number of times that the walk leaves I before stopping. For example, we have a vertex I, the expected number of times that the walk leaves state I. For example, the first time that we leave I is this, and then we come back, and the second time that we leave I, the third time that we leave I, the fourth time that we exit I. So it's the exit frequency, and sometimes we go out and come back, and sometimes if we go out and come back to state I. And so we just count the number of exits from I. And the expected number of times that the walk leaves state I is just the exit frequency. So now we are ready to prove the theorem. So we define the we define the exit frequencies, and just we write nu of X is the expected time exit frequency. So we are it's a counting problem. We are counting the number of times that we hit X. We can say like that. K is equal to from 0 to S minus 1. And because mu is a initial distribution, so X is rho, and let's write and see what happens to this. So this is what we want to evaluate to see what is this. K from 0 to S, so we know one thing. We know that the initial distribution, it means that at initial step, it is just mu of x. So what we are left with is just expectation of k after 1, k from 1 to s, because we know the initial distribution is mu. So what we are left with is this. But we can say that this is the, according to this definition, this is just the sum over nu y, p, y, and x. Summation over y. So this becomes expectation of k equal to 0, k from 0 to s minus 1 of xk equal to x plus rho of x. Because at the stopping time, we have a distribution rho. So plus at finally, we know, we know the initial distribution and final distribution. Initial distribution is mu, final distribution where we have stopped is rho. So if we just write this, it means that, so if we just simplify whatever I have written is just, we can write just one line that mu of x is nu of y, p of y, and x. So this is just for one stopping time. And let's imagine that t is another stopping time, so that we have the same, so we have used rho for both stopping times s and t. So now we imagine that we have another stopping time, and it happened that their distributions are the same, and we want to see what happens to our equation. So let nu prime of x be its exit frequencies, because this is another thing. So this could be its exit frequencies. And for the same reason, it should satisfy this equation p of y and x. And if you subtract those two equations, so the last equation was nu of x plus rho of x equal to mu of x plus nu of y, p, y, and x. So if you just subtract these two equations, you will see that you can easily observe that nu prime minus nu is equal dp. And this is the matrix version of that, because nu at x is just a scalar, but if you evaluate it for all vertices of your graph, then it becomes a vector. So this is, by definition, we call it d. And d is equal to dp. Isn't it familiar? So it has, so it should be proportional to your stationary distribution, because this is something that only stationary distribution satisfies. So d should be a constant factor of your stationary distributions. So here imagine that we have z, and we have some stopping time that, for example, getting out of this boundary, and so the number of times that visits this point goes out sometimes, and But in order to reach z, it should cross the boundary. So from this equality, we can observe that d should be proportional to stationary distribution. And nu prime minus nu is alpha pi. But we know that we say that there exists some z such that nu of z is equal to 0. That z that I showed you on the picture that I showed you. So this is equal to alpha p of z, but this term is 0 because we have told you that there exists some z such that nu of z is 0. And from this, we can observe that expectation of t is equal to nu prime of x, and this is greater than nu of x. And what is this? This is just the expectation of your stopping time. It means that we have proved the theorem because it is the minimum, because your stopping time t, this value is greater than our minimal stopping time. So we have proved this theorem. So you see, it's just using some subtraction, we have proved that theorem. But now I want to focus on probability spaces in ZD. So our random walk is on ZD. For many reasons that I told you in the previous lecture, that if our space is complicated, we want to go to see if we can relate it, if we can use the dual problem for the primal problem. For example, your dual problem, ZD, everything is easy to understand, and we have good measures. But in the primal problem, you have a weighted graph. It's so complicated. And it is a general weighted graph. So we want to work for all instances, instance in the sense of computer science. So for all instances, it's very hard because it is not planar graph, it is not infinite tree, it is not some restricted class of graphs, such as Ramanujan graph. It is not restricted to some sort of some example of expanders. So it's very general. That's why we should go to the created dual problem, which life is easier on that, and then we can come back. Just we go just in electrical engineering or image processing. If something is hard, we go, for example, in signal processing, if we have some functions which is difficult, we go to Fourier space, we do Fourier transform. Or if it is discrete, we do discrete Fourier transform, if it is a vector, and then we come back by inverse Fourier transform, inverse discrete Fourier transform, inverse Laplace, and for example, Mellin transform. For example, in finance, we have Mellin transform and many different transformations, and all of them are related to harmonic analysis, which is a generalization of these basis functions, and it is related to Hilbert spaces as well. But so imagine that our probability space is just, we have a filtration and the probability and probability space in ZD. And the probability, for example, in 2D lattice, in 2D, for example, we go there are 4 states that we can go. For example, D is equal to 2, then the probability that xj equal to E is just the unit vector, and this is equal to 1 over 2D. For D equal to 1 or here D is 2. So this is